So our first speaker is Professor Daniel Rittel from the Faculty of Mechanical Engineering at Technion in Israel. So Professor Rittel, if you're here, the stage is yours. Go ahead.
I am. Thank you very much. Okay. Well, good afternoon, everybody. Do you hear me?
Yes, you're very clear, yes.
Okay, excellent. So first of all, I would like to thank the organizers for considering me and inviting me to present a talk about experimental work we've been carrying out. I will address two completely different subjects, starting with metals and ending with soft gels. And these are two mainstream subjects in my lab for the moment. But first of all, I would like to wish Professor Simha a very happy retirement. And I'm not surprised that my predecessor, Dr. Lovinger, noticed that Simha in Hebrew means joy. So I will not repeat the definition, but I think the name is appropriate and conveys with it the best wishes of joy, success, and happy retirement. So first, I would like to acknowledge, of course, as I said, the organizers who invited me and the European program outcome, who generously supported me, as well as the Israel Science Foundation. We'll start with a little bit of tourism, which is maybe relaxing those days where tourism is severely limited. So Technion, the Israeli Institute of Technology, is the older Israeli university, and it started long ago at the foot of the Carmel Mountain. This is the Carmel Mountain. This was at the foot of the mountain. This is the
Professor
original.
Rittel, would you be able to go into full screen mode if you don't mind? Sorry to interrupt.
I could try that. Yes, definitely. Okay.
Perfect.
So yeah, that's the historical building that was founded in 1912. And seen from the upper part of the Carmel Mount, this is what we see from the campus, a bird's view of the campus with the Mediterranean Sea here. So it's a very nice view, unfortunately with too much industry, but that's another story. We have 17 faculties, one school of medicine, and around 14,000 students in science and engineering. We have 3 Nobel laureates in chemistry on campus, and it's funny enough to recognize that none of them is a chemist, actually, but they have a Nobel laureate in chemistry. Some nice places to visit in Haifa, the very famous Baha'i temple, the Baha'i faith, which originated in India. And the Baha'i community is very present in Haifa because Haifa and Acre are the places where the Baha'i prophet lived. So they created a wonderful suspended gardens, which is an absolute wonder to visit. Then, if you go a little north, you will come to Acre, a very ancient city back to the days of the Crusaders and before. Now it has always been a port. And the interesting thing about Acre is this is one of the places where Napoleon, the French emperor, started the campaign of Egypt. He landed in Palestine in the town or city of Acre. And maybe another nice point is the Sea of Galilee, which is a small drive, short drive of 45 minutes, called Tiberias. Another very famous place because Jesus is reported to have walked on the Sea of Galilee in one of his many miracles. And therefore, this is a place of pilgrimage where many Christian pilgrims come to get baptized on the footsteps of Jesus. So as you can see, many interesting places that you're all welcome to visit as soon as this COVID thing is over, what we hope soon. Another place which is no less famous, of course, is Nazareth, where Jesus Christ was born. So it's also a very important place for Christianity and for humanity in general. All this is within 30 minutes, 45 minutes drive from Haifa. So now I would like to talk more specifically about my lab. The lab which I developed is basically an experimental lab, an experimental group with a strong numerical component in which we investigate the thermomechanical response of materials at high strain rates, dynamic properties of materials, constitutive testing, failure modes, failure mechanisms, scanning electron microscopy. We also do dynamic fracture mechanics and look at the response of cracks subjected to impact loading, stress intensity factors, and so on and so forth. And the last point, which is a little less active those years, is structural health monitoring using a variety of techniques such as electrical impedance tomography that we developed. The research themes in a nutshell were dynamic fracture mechanics, thermomechanics of dynamic flow and fracture, in which we are specifically interested in the thermomechanical conversion, and I'll be at high strain rates. I'll be touching upon that in my talk. Shear localization, which is the half of my presentation. And then dynamic and ballistic behavior of polymers, or scaling issues and blast experiments. We're also interested in developing new experimental techniques, high triaxiality, low triaxiality, dynamic testing of the fracture and response of advanced ceramics and their relationship with the microstructure, wave propagation in gels and soft matter that I will be touching upon shortly, and various other topics then you can read for yourselves. And maybe the last one, last but a little bit foreigner to all these activities, the recent activity in biomechanics of dental implants. I got interested in dentistry, and now I do a lot of work on modeling the bone implant interface and studying the fracture of dental implants, a field that is very active in India, interestingly. So, about our talk. I want to talk about two subjects. The first one is adiabatic shear failure, and show you experiments, basically, and what can be learned from experiments. And we'll talk about thermomechanics and propose a failure criterion. And the next part, which is not related, would be about thermoreversible gels and their shock energy absorption capability, which is quite interesting. So, adiabatic shear failure, what is that? Well, it's a material or structural instability in which homogeneous deformation all of a sudden becomes heterogeneous, localized into shear deformation. And you get what people call a adiabatic shear band, or a narrow band, which in fact is a plane. It's not a band, it's not two-dimensional. But when you perform metallurgical sections, it looks like two-dimensional. Well, the first one to have reported about that, to my knowledge, is Tresca in 1879. So as you can see, the subject is not really, really new. It's observed in many metals, polymeric materials, and even earthquakes to some extent, in which we have a strong shear component. And there's a very good book by and Dodd, two books actually, that summarize the state of the art on the subject. Okay. If you shoot a blunt projectile onto a plate, what you will see is a plug. You see, there's a plug being ejected. Well, the boundaries of that plug are, in fact, an adiabatic shear bend. But the same would occur if you machine a metal. When you cut a metal by machining, in fact, delineate a couple of shear bends, and this is what you are cutting on. This is how you're cutting the metal. And if you want to look at the overall picture, that's the way it looks. Your blunt projectile and the plug that is ejected with those boundaries of the adiabatic shear bend. So in other words, what we can say for a shear bend is a local heterogeneity in the sense that it concentrates strain very sharply in an otherwise homogeneous neighborhood. Here you have a homogeneous neighborhood in China, and you have your heterogeneous guy here who doesn't belong. And that's a shear bend. So let's talk a little bit about the adiabatic shear. The conventional wisdom has it that strain rate hardening, that has been talked about quite a lot today, and thermal softening that has been evoked are in fact competing. And this is due to Ziner and Holman, 1944. So if I plot a stress strain curve, and that's what I get at low strain rate, I increase the strain rate, the material is harder or stronger, but its capacity to strain harden decreases. And eventually, if I increase the strain rate even more, the material is stronger, but then loses its hardening capacity, starts to soften, and becomes unstable in the sense of plastic deformation of materials. And when it becomes unstable, this is where you can expect a shear bend to develop. So the accepted criterion, because this is an instability, and you still need a criterion when you do calculations, and you would like to define a failure criterion for your calculations. So the accepted criterion is that of a failure strain. So people put a failure strain, and they believe that at a certain strain, the material will localize. And that's okay for me. So let's start with the role of temperature, because temperature is the prime suspect. And as the strain rate increases, the temperature, the heat generation increases, the temperature rises because of adiabatic conditions. And therefore, the material softening occurs, which leads to loss of stability. So we'll start by stating the obvious, that thermomechanical coupling causes a homogeneous temperature rise prior to localization. And here I want to emphasize the point that I'm talking about what brings about to localization, and not what happens once you have the localization. Indeed, from a spectacular point of view, the post-localization failure is very dramatic, with temperatures in the range of several hundred degrees inside the band. But the question as an engineer that you would like to ask is, how does the story start? Why does it start? Can we prevent it? Do we have a criterion for it? So as long as deformation is homogeneous, then you have a homogeneous temperature rise in your solid. And then you can say that the mechanical energy is transferred into heat. That's long known. Well, one should say here that it's partly transferred into heat, not totally transferred into heat. And here we can define the well-known Taylor-Quinney coefficient, this one, the integral, which is the ratio of the thermal work to plastic work. With the years, it has become evident that, contrary to what Taylor and Quinney measured or hinted, this is not a constant. And the early work of Ravichandran at Caltech and co-workers has shown that, in fact, it's a function of the strain and the strain rate. Later work looked at this coefficient, but from the following point of view: a ratio of powers, thermal power to mechanical power, because it occurred to me that what you see in the coupled heat equation is this coefficient, what we call the differential coefficient, in which the coupled heat equation, the differential equation, is in fact invoking a ratio of mechanical powers and not mechanical energies. And then there's a sort of confusion in the literature and the authors, in which people are just considering one Taylor-Quinney factor and they're not referring to the differential. So what happens with the integral? Well, by the first law of thermodynamics, you cannot generate more heat than you invest work. So this has to be smaller or equal to 1, and that makes sense. Okay, but the differential is a time shot. It's in fact a series of time shots of the process, and you can show and you can measure that at some stages this ratio exceeds 1. This ratio can exceed 1 without violating the first law of thermodynamics. But on the closed cycle, on the integral sense, you will never exceed 1, unless, of course, if you have extraneous sources, and I won't elaborate. So since the temperature is a key component of the story, we want to measure the temperature in real time using infrared monitoring. Infrared monitoring, well, is based on using an infrared detector, which doesn't suffer the limitations of an infrared camera. In terms of response, you can go very fast, several mega samples per second, but you're sampling 1.1 pixel or more. So this is a bit of a delicate technique, so it's not very popular. But let me show you some typical results. We have three channels, three active channels. We're testing titanium 6, aluminum 4, vanadium. And in blue, you have the stress strain curve. And those three lines here are the temperature rise. And the dashed line is the one that you would obtain would you convert 100% of the mechanical energy into heat. Okay, so we can measure in real time. Here the strain rate was about 3,000 per second. We can measure the temperature of a deforming gauge of a specimen. And what do we see here? Well, we see something which is a little bit curious, is that if you believe that localization here occurs here at final failure, that the shear band forms and propagates as a crack at final failure here, then you notice that the temperature rise is relatively modest. And this was reported by Marchand and Duffy, actually. Well, this was one of the inherent limitations of the detector. But if we, for a minute, forget that, they said that nothing is happening during most of the tests, and the temperature rises only at the end. This has been, in fact, forgotten or neglected, and we brought it to light again. Because if the temperature rise is negligible prior to final failure, that casts a question upon thermal softening. If there is no temperature rise or no significant temperature rise, then where does the softening come from? That's the first question. Then we, much later, with a former student of mine who's now a postdoc at Oxford, we asked the following question. If I take a material and I perform tension tests, a compression test, dynamic, of course, and shear tests, which I will elaborate a little bit upon them, and I measure the Taylor-Quinney coefficient, the integral one, and these are the materials, titanium 6,4, CP-Ti, and a series of other materials, and take my word for it that there are a few more which were not included in that paper. Then what I can see is that for if C is compression, T tension, and S shear, for most materials within experimental error, all three modes of loading are equivalent. And well, that just tells you that von Mises is not a bad approximation for that kind of plasticity. However, for commercially pure titanium, we apparently have a problem because compression and shear give you one coefficient and the other one in tension is much lower. So we wondered about that, and the answer was pretty straightforward. When we did metallographic sections or metallurgical characterization of the specimens, we saw in compression and shear a lot of twinning. The twinning was absent in tension. So we came to the conclusion that twinning is a strong heat generator, and that was already noticed in another context by a team Chicago by Padilla and John Lembros. They reported that. So one cannot dissociate the thermomechanics or the thermomechanical coupling from the deformation micromechanisms, and we're back to metallurgy at the end of the day. So not all materials are symmetrical, and pure titanium is one of them. And that has been noted in the literature in another context of yield surfaces in the work of Oana Kazaku, for instance, and Frédéric Barla. So we reported that the Taylor-Quinney coefficient, first of all, is not 0.9 as universally accepted following the pioneering work of Taylor and Quinney. It's not 0.9. It can have various values, smaller values, and that depends on the material and sometimes on the loading mode. So if you add to that this coefficient may be or is rate and strain dependent, then your heat equation becomes nonlinear. The coupled heat equation becomes nonlinear, where you need a separate equation for your thermomechanical conversion, and things become interesting. So we said Taylor Queening coefficient is 0.9. The temperature recorded prior to localization remains quite modest, of the order of 50 degrees. That's not very significant to soften the material. And there is a strong relation with the mechanism of deformation. Would it be twinning or slip, or both? Thermal softening, question mark. So let's look at some experiments we performed in order to understand better the phenomenon of shear localization. So what we did was to take specimen, and we knew the static failure strain. So what we could do was to quasi-statically load or preload the specimen, unload it, and then impact it, and record the static and dynamic curves. So that looks a little bit dense, but look, for instance, at those are stress strain curves. Look at the black curve. That's a monotonic dynamic test. This is the failure strain. Let's call it the failure strain. Let's look now at the green one. We load statically here. I hope you can see my mouse. We unload, let it cool, and then we reload dynamically, and then the total strain is, of course, larger, and so on and so forth. So is there a critical strain at failure? If we take into account the overall thermomechanical history of our material, we cannot define a unique failure strain. Let me translate that into engineering terms. I am machining an armor plate, and I'm cold rolling the plate. And then I'm asking you, is that cold roll plate or hot roll plate, is it going to perform as well as a plate that was not rolled before? And this is the what I would say, this is the rolling, this quasi-static pre-strain. So at that point, we wonder, what do we do with those results? In fact, there's no unique failure strain, and we have to take into account the quasi-static preload history. So what we do here, we jump one step, and we calculate the integral of the stress strain curve in the dynamic regime only. We simply do not consider the quasi-static phase, but we plot this energy, this dynamic energy, as a function of what was the quasi-static pre-strain. And here, to our great surprise, we discovered that, well, up to a reasonable extent, it's rather constant. Of course, it will fall at very large strains, but for a whole range of strains, which differs from material to material, because we have tested, of course, several materials, this energy remains constant. So that's interesting. That could be a criterion, because strain energy density is also a criterion. So now let's summarize. We have our balance of dynamic energy, which says that the mechanical energy is the thermal energy, WT, and the remaining energy, which is called the stored energy of cold work, and that is the energy that is related to the microstructural rearrangements of the material. This subject is giving rise to a very noticeable interest in the very recent literature in plasticity value. So part of the energy is stored in the material. So if we said that the mechanical energy as a first extent is constant, and then if we see that the thermal energy doesn't play a significant role, then we're left with the stored energy of cold work. Precisely those 1 minus 0.9, those 10% or more, that are universally ignored, because we're always looking for a temperature elevation. We're not considering what is stored in the material. And the stored energy of cold work has a very attractive feature. This is the microstructure of the material. And whereas so far you had a very large number of metallurgical papers on shear localization, and a very large number of mechanical papers on shear localization and perturbation models, there was no relationship between the two, because the continuum mechanics could not relate to the microstructure. So here, using a strain energy density concept, you can relate to the microstructure, and you can dive deep into the twins and the dislocations and so on and so forth. And this is what people are doing those days. So we reported this first review in the Physical Review Letters in 2006. So That was 14 years ago. And the more we work on the subject, the more we discover and the more we understand that we don't understand very much. So now the question, when does shear localization start? Well, of course, you could tell me it starts when your stress strain curve collapses. That would make sense. Well, let's check it anyway. So for that, we perform interrupted tests. We simply put stop rings on a Hopkinson bar, use a very nice specimen, the shear compression specimen that was invented in 2000 at Caltech with my colleague and friend, Professor Ravi, and Dr. Sang-Wook Lee. And this is a specimen in which the kinematics enforces a state of dominant shear, but not pure shear and not simple shear, but dominant shear. And you can use this specimen statically and dynamically alike, perform some shear dominant experiment. Well, if we look now, we go all the way down to the transmission electron microscope, look at the microstructure before. We see grains using the transmission electron microscope. My friends and colleagues call that all kinds of names, alpha prime, beta phase, and everything. Not relevant for us now, but the interesting picture is this one. We have coarse grains, and we see the electron diffraction patterns indicating a coarse microstructure. Please keep that in mind. Then we go to the failed area where we have a shear band. And if we look inside the shear band, we see a lot of black and white features that we don't really know. Those are dislocations, but what more? But the dislocation, the diffraction patterns are completely different. Look, they are very dense and lots of small dots. That tells you one thing and one unique thing. The microstructure is extremely fine, and you have here nanograins. Okay, we have nanograins. Where do they come from? How did they form? But they are here in the shear band. You have those nanograins. Am I telling you something new? Well, I'm sorry to disappoint you. No, this is not new. This is very well known that inside the shear band, the microstructure has evolved and grains have recrystallized dynamically. That's the term, dynamic recrystallization. And you now have nanograins of a few 10 of nanometers in size. Whereas at the beginning, we were talking about tens of microns. Now it's tens of nanometers inside the shear band. Okay, that's not new. What is new is what I'm going to show you here, because this specimen was not broken. It was loaded up to half, only half of its failure strain, stopped and sectioned. If there was a small temperature rise at failure, at half of the failure, there was no temperature rise. But again, look at this diffraction pattern, and you see your nanograins are here again, and you can see some of them. So in fact, you can understand that nanograins formed way before failure. And you can go even beyond and say that, in fact, this phase transformation is the precursor to failure. Then such grains are, in fact, producing the shear bend because, on the one hand, nanograins, they are stronger than the surroundings. That's the whole patch effect. But on the other hand, they have absolutely no hardening capability. That was shown already long ago by my friend, Katie Ramesh, who's here with us today, who showed the series of beautiful papers, and one especially on iron, coarse grain and fine grain. And he showed that the fine grain, ultrafine grain iron was prone to shear localization with very little strain hardening. So here you have the same thing, in fact. So this specimen did not fail, and well, qualitatively at midway to failure, we already have the final microstructure. There's no new mechanism that operates until failure, and one should therefore look for a quantitative evolution of this recrystallite phase. That's a little bit difficult. That's work in progress for the past 10 or more years. So here we reported that result as blaming dynamic recrystallization as a potential cause. Because in fact, if we're looking for a microstructural, for a softening mechanism, this is your softening mechanism. It's not thermal, it's microstructural. So if you can control it, you can control the propensity to dynamic failure. Conclusions. Adiabatic shear has, first and foremost, microstructural origins. That's what we believe. The evolution of dynamic recrystallization and kinetics must be further studied. and the interaction with twinning must be taken into account. Dynamic recrystallization, in fact, is driven by the stored energy because, as noted by Taylor many years ago, there's a limited amount that you can input in a material before something happens. And this stored energy, like fracture, and this stored energy is, in fact, we believe, the thermodynamic driving force for the phase transformation that softens locally the material. And something that we did and we still do is macro modeling based on the strain energy density and damage criterion. I will not discuss that for now. And that ends the first part of my talk. The second part of my talk is about impact mitigation with hydrogels, and this is work carried out with my colleagues, my former student, Jonathan Rothbaum, Dr. Galit Parvari, and Professor Aishen, both of them from chemistry at Technion. What is the motivation? Blunt shock trauma. You see, that's a modern fighter, and he has all kinds of protections and boron carbide plates and a strong helmet and whatever. There's one thing that this fighter is not protected against, and this is the elastic precursor. And when you experience a shock, the first thing that propagates and the fastest thing that propagates is an acceleration, elastic acceleration wave, and the damage and destruction of your protection comes much later. But at that stage, the brain has already been, the brain, the liver, the heart have been violently accelerated. And it is not a boron carbide plate or an alumina plate that are going to protect you or your head against the shock. On the contrary, they're very good waveguides or wave propagators for elastic waves. And this is a typical fighter. By the way, this is this guy. So this is my student, and I took my former student, Dr. Rothbaum, and that's his picture. Okay, so now let's see a curious material, these methyl cellulose hydrogels. Well, what we know is that most materials start solid, they liquefy, and then they become gas. That's what we know. The inverse freezing gel that I'm talking about starts solid at low temperatures, become liquid. And then when you heat it, it solidifies. And only when you heat it more, it liquefies. So there's a liquid to solid phase transition that is not observed in other materials. That's what we call it inverse freezing. It's totally reversible, totally reversible. And there is a family of inverse freezing materials like that. The chemists know that for long. Where is this material used? Well, don't laugh at me. It's food industry. This is used to simply densifies all kinds of sauces and decorations on cakes. So this is completely benign material. Okay, quasi-static compression. First thing, you see repeatability. Repeatability of the stress-strain curves. Homogeneity, just meaning that we cut here, we're testing the solid specimen. So the tests are carried out at about 70 degrees C. If not, you have a liquid. And homogeneity, we want to see that the cylinders that we test are homogeneous, and they are. You see, that's your gel test in the solid state at 70 degrees C or shortly after. In a few minutes, it will become completely liquid and forget whatever happened to it before. Quasi-static compression as a function of concentration. We had yesterday a nice presentation by Professor Alan Zender, who was discussing the mechanical properties of hydrogels. So these are other mechanical properties of other hydrogels at various concentrations in the solid state. Well, the material hardens with temperature. That's again something that we materials people or mechanicians are not really used to see, that as you increase the temperature, you see from 65 to 100 degrees, your material becomes stronger. Of course, don't push much beyond because it will become again liquid. But it means that if you're using this material for any purpose and you leave it in the hot sun of Israel those days and you're afraid that something will happen, don't be afraid, it will only solidify and become stronger. Quasi-static compression, strain rate sensitivity? None. As you can see, there's no real strain rate sensitivity. Dynamic regime, well, that becomes a little more exciting here. We have to test a soft material. So using a Kolsky bar, is nice, but it's not sufficient. The strain gauges are not going to react mostly on the transmitted part. So what we use is force transducers by the name of FlexiForce, piezoresistive force transducers. And we measure directly the forces on both sides of the specimen. We started with that with ballistic gelatin several years ago, and now we're onto those gels. And the thing that you see here is basically a furnace, because again, you need to, a furnace with water, because you need to hydrate your material. If you heat it without hydration, then it will simply desiccate. So this is a close-up. Those are the heating wires, but the specimen is here, in fact, and those are the FlexiForce wires, leads, sorry. Dynamic compression, again, repeatability at various strain rates. Generally speaking, the curves are nicely repeatable given experimental uncertainty. Well, static versus dynamic, there's, as expected, a very strong difference. The dynamic behavior, of course, is significantly better or higher or stronger than the quasi-static, but it's also less ductile, and failure occurs at small strains, whereas under static strain, loading, you can go for very large deformations. Okay, so that's the plus and the minus. You have a stronger but less ductile material. What I call linear attenuation, ultrasonics. You apply very, very weak signals that was alluded to in a talk that I listened to yesterday, and you simply analyze the various reflected pulses and you calculate the attenuation. And that's your attenuation as a function of frequency, and that's the result. So first of all, you do that with water, brass, steel, PMMA as a function of frequency. See, the frequencies are relatively high, of the order of 10 to the 5, 10 to the 6. And this is the attenuation or function of frequency. And then you go to the gel. You go to ballistic gelatin. That's a well-known solid. And then you go to the gel, 5% in black, 10%. So it's mostly water. You have to realize that this is mostly water. 5% gel is water. And the attenuation, the linear attenuation, ultrasonic attenuation, is rather high. We will not pursue here the quantification of the complex moduli of the material. We just want to know the attenuation. So that's the linear attenuation. Let's go to a more exciting part, the nonlinear attenuation, in which you apply a shock and you would like to see the attenuation. A priori, it's not supposed to be the same as the linear one. So again, you use your setup of a liquid sample now. We have a liquid sample, 2 sensors, and you sample the back and forth, the back and the front and the back forces with your sensors. Start with water, as always, no attenuation, that's expected. Okay, as a function of the frequency, that's the power spectrum. Go to a 5% methyl cellulose solution. Look at that, the force has been significantly attenuated. Red is the front force, and blue is the back force, I think after 1 or 2 centimeters. Look at the power spectra, the high frequencies have been attenuated. Look at the blue one, it doesn't transmit the higher frequencies. Note also something interesting. The range of frequencies I'm talking about are the hundreds, 100 and less kilohertz. Those are structural frequencies. Those are not ultrasonic frequencies. They're very low frequencies of the kind that we would like to mitigate in a structural shock. So we have the 5% and the average force reduction, 35%, average impulse reduction. Of course, those numbers have been refined and we're still working on generating much better statistics than those results. If we increase the solution to 10%, then we reach a very strong attenuation of the force and the impulse reduction. So this material, which is basically water with a little bit of powder, has a very strong shock attenuation power. How does that come? Where does it come from? That's the liquid, that's the solid, okay? So what do we do? Well, shock-induced gelation, that's what I want to talk about. Gelation is usually the realm of temperature. You increase the temperature, you have a slow process, your gel solidifies, but in a few minutes for a typical size of a sample. It takes a few minutes. So what do we do now? We use a high-speed Kirana camera. have a chamber, we have one Hopkinson bar, it's full of gel, and we shoot. As usual, okay, we look for turbidity that will indicate some phase change.
Professor Rittel, we have 5 more minutes. Sorry to interrupt.
Okay, I will start accelerating. I'm almost done. We compare with water, we compare with ballistic gelatin, and then we go to the gel. Water, at various times, nothing. You see, there's nothing. Nothing happens. Ballistic gelatin, you look, nothing. With time, nothing. You go to the gel, you go to the methyl cellulose gel, and here you're surprised. You see a white blob here, close to the impacting bar. There's a white blob. That would indicate solidification. Now let me show you a movie. So you will see white forming here. I hope you all see the white. I will not have time to replay. And this is a shock-induced gelation that takes place in a few microseconds. That was not known before. And that makes sense. That makes sense because in fact, what you need to solidify your solid is energy. And be it thermal energy or being shock energy, all you need is energy. So we reported that also. So let's summarize the energy, the linear, the nonlinear, and the linear. Of course, there's no overlap in terms of frequency. Ultrasound is always much higher. And we now have the basic characteristics of the material, and we run experiments. That stage, I should mention recent experiments with my friend and colleague, Professor Aaron Shukla, who's here with us today, who will witness that in his lab with his shock experiments using shock tubes, he also got the same results that we got with the Hopkinson bar. So let me conclude. Methyl cellulose gels, well, the mechanical response is highly dependent on the gel concentration and temperature. They have improved mechanical properties at high temperatures. That's contrary to regular materials that tend to soften. Ultrafast gelation, that's a new phenomenon. Acts as a hardening mechanism and as an energy dissipation mechanism, because when you solidify, the material absorbs energy. Well, those materials have a significant capacity to absorb energy and to mitigate forces, even at low frequencies, structural ranges. And the endothermic shock-induced gelation can reduce significantly the impact forces. That's something that we measured as I was showing you. So those materials, in fact, have a very strong potential to mitigate energy or to become part of armor of protection systems, which protect the person or the structure against the shock and destruction, but don't protect it against the propagation of elastic waves that could be very damaging to the human body. With that, I want to thank you for your attention, and I'll be happy to take some questions if I can.
Kaushik, can I ask a question?
Yes, please. Thank you so much, Professor Rittel. We have a few minutes actually for a few questions. So, Professor Aaron, go ahead.
Yeah. Danny, very nice talk. This is Narasi here. Excellent talk.
How are you?
How are you doing? Yeah.
Thank you.
Yeah. So I had a question on the first part. You showed an experiment where you, in a dynamic test, where you interrupted it at 50% of the failure strain. How do you do that in the dynamic test?
Okay. We use the first of all, we use the shear compression specimen that I was showing earlier, and we just put a stop ring on the bar. That's a very simple engineering thing. You put a stop ring. I don't know if you see my hand here, but if you see my hand, you put a stop ring on the bar, and then your specimen can deform to a predefined level before your bar hits the stop ring and everything stops.
Okay. Thank you.
You're welcome. Yeah, that's the specimen. So you can control the deformation, and that's a very useful technique.
Okay,
Thanks,
we have a question from Ishwar in the audience.
Yeah. So Dan, very interesting talk, and I also have a question from the first part of your presentation. You are saying that when the adiabatic shear band forms, you say that the crystallization of nanocrystallization happens due to the microstructural softening, not the thermal softening. Is it
not exactly?
Yeah.
Not exactly. Let me rephrase. Maybe I was not clear. I'm saying that, in fact, this recrystallization occurs because of the stored energy, because of the part that is not dissipated thermally.
Exactly.
And this recrystallization induces islands of softening.
So the local temperatures could be as has the DRX domain, right? Close to 1,100 degrees centigrade. What are the approximate temperatures rise?
So,
What could be the approximate temperature rise you're thinking about in titanium Ti6 alloy?
well, I'm not sure I understood, but
No. So what could be the local temperature increases?
Okay, so the
With,
temperature increase that I was showing, and we've done tens and tens of experiments like that, including at Caltech. And this is typically what we always find. Prior to complete failure, the temperature rise is extremely modest. It's a few tens of degrees. It's only once your shear band has formed that you will see several hundreds of degrees that have been reported long ago by Duffy. But prior to collapse, prior to final collapse, the temperature rise is extremely modest. And that's in a series of materials, various materials, and it's almost always the same story. So you have two mechanisms, in fact. I'm not saying that there is no thermal softening, but let's say it like that. If you have a material that can recrystallize, it will fail early. If you have a material that is soft, it will go to very large strains, and by doing so, it will generate a lot of heat, and then thermal softening plays a role. So it's a competition, a complementary competition between microstructural and thermal softening. It's not only microstructural and it's not only thermal. It depends on where your material fails. For instance, if you take a very strong steel, like maraging steel, it's very strong, but the failure strain is of the order of, say, 10%. You cannot expect, and it generates shear bands. You cannot expect a homogeneous, significant homogeneous temperature rise with a limited deformation of 10%.
yeah, thank you very much.
Oh, sorry.
Okay, we have one more question from Vishnu in the audience. Vishnu, can you just ask your question directly? You can just unmute and ask.
Hello, am I audible?
Yeah, go ahead.
Hello, Professor Rittel.
Hello.
Can you hear me? Yeah, actually,
Yeah, go ahead.
yeah, my question is, may it be thermal softening, structural softening, or whatever it is. So what is the quantity of softening we needed to get the shear bands? Is there any quantity or any softening is enough? Or some
Well, Vishnu, you're asking me a very tough question. Thank you for it. I don't have the
actually,
answer.
in fact,
I don't have the answer. There is
actually,
no
why I asked the question? Sorry.
well, I will give you.
Actually,
I will give you an academic answer.
yeah.
If I were a mathematician, I would tell you that the smallest perturbation is probably enough to trigger the mechanism. The smallest perturbation, half a degree, that would be heterogeneity. Then you would do a perturbation analysis to see if this perturbation is leading to a global instability. As a metallurgical engineer, originally that's what I am, I know that in order to significantly soften a material, you need to reach, let's say, back of the envelope, half the melting temperature in absolute, in absolute homologous temperature, T divided by Tm, roughly. Because softening, material softening, is related to diffusion in a material, and diffusion does not kick in before half Tm. So you get now the two extremes. The mathematical answer, which has any slightest perturbation, can be a problem, and the engineering answer, which tells you that as long as the temperature rise is not significant, global softening is not expected to occur. And that excludes, of course, one thing, which is called the hot spots. That's another problem for discussion. Are there hot spots? Means simply that you may have very small and very hot spots inside the material, very localized heating, which we've never seen, but you could suspect it. And people who deal with explosives, for instance, they're very familiar with the hot spots because this is what ignites an explosive. So if there are such hot spots, they should be considered. We didn't see them, but that's due to the spatial resolution of our detectors, which is of the order of 30 by 30 micron.
Okay. So actually, why I have one more extent of this question. Can I ask?
Yeah, please go ahead. Go ahead.
Actually, why I am asking this question is I am actually simulating the thick walled experiment, which is behind your screen. I mean, behind what is showing actually with small, thermal softening. Not even small, with an extent of thermal softening. Also, I was not able to generate, the shear bands.
That
But
I think you should ask Dr. Lovinger if he's still listening, because this was part of his PhD and he started
yes,
with
actually,
those
I've been.
simulations.
Yeah, I'm extremely referring to his paper. I know, I'm aware. So
No, but I
actually,
think he's much more knowledgeable than I am, because he struggled with thermal softening to come to the conclusion that that was not of any help in the numerical simulations. Maybe I'm distorting a little bit, but that's what I remember.
yeah, I understand. But as in the beginning of your discussion, you said it's a competition between thermal softening and the strain rate hardening.
Yes. That depends very much on the material. You see, in order to generate heat, you need sigma and you need epsilon. We agree. Usually materials have sigma, they don't have epsilon, or they have epsilon and they don't have sigma. At the end of the day, it's an integral. So you have to make your choice. What brings you the maximum temperature or most of the temperature? And if you take a pure material like we did with pure aluminum, we reached strains of six. That's huge. And there was no sign of localization whatsoever. And it's even worse. The microstructure of the grain looks completely pristine, like nothing had happened on this grain. So on this material. So there are still quite a few interesting questions here. But in terms of heat generation, remember, you need sigma and epsilon. You never have both. You never have very strong and very ductile material. But if you have them, you will generate a lot of heat, that's for sure.
So the thermal softening may not be the sole, the unique reason for shear bending.
Exactly. That's my position.
Yeah. Thank you very much.
My pleasure.
Thank you.
Okay, thank you very much. If there are no other questions, Dr. Lovinger, do you want to just add to the discussion for a minute? Hello? We can't hear you. Okay, maybe we can just have the discussion go on in the chat, in the Q&A window at the bottom. So thank you so much, Professor Rittel, for a wonderful talk and for joining us in this 3-day event.